I hope everyone's doing well. I am Mr. Ish. Thank you for joining me for this very interesting video where I promise you will learn quite a bit. We are looking here at a limit evaluation, the development of that limit, and then the evaluation of that limit and the significance behind it. A limit as a certain angle theta approaches 0 from the right. I have in the numerator r theta. In the denominator I have r square root 2 minus 2 cosine theta. What does all of this mean? If you look over here at a portion of a unit circle, which is basically a sector, you have a certain angle here theta, you have a certain radius, you have a certain arc length that is equal to r theta, and I'm indicating as this. That's my numerator right over here, an arc length between these 2 points right here. This point you know is going to be r comma 0 because it's a radius units away from your origin. What's this point going to be? It's a certain x comma y point on your unit circle, and you know parametrics comes into play. If you develop this in terms of a right triangle, here's your angle theta, and you know your sector is projecting beyond that. You have a certain x, you have a certain y, you have a radius. You know cosine theta is equal to x over r, and then you know x is equal to r cosine theta. You know sine theta is equal to y over r, and therefore y is equal to r sine theta, and these give you your x and y values of that point P. So we have it, and you've seen this so many times. So what does this denominator item represent? It represents a certain length of a segment from this point to this point. The segment which subtends the arc by means of that angle, and I'm representing it as an S with a straight line. So when we're looking at this, we're looking at a certain arc length divided by a certain segment length, but they're both originating from the same point. Keep in mind, anytime you have 2 points and you're connecting them by means of an arc, and you're also connecting them by means of a straight line, the arc will always be longer in terms of dimension than the straight line, the segment. And you can imagine the value here in the numerator is slightly larger than the value in the denominator, but as this value of theta becomes less and less, approaching 0, that difference between the two becomes less and less, so the ratio of the two approaches 1, and that will be the end result of this limit, and I will prove to you why that is the case. Why is this a one-sided limit? Because we're approaching 0 here only from one direction. It's a single-sided limit. From positive values, we're approaching here towards 0. So we have the value over here for x and y, and you can see this is my px, my py. How can I determine this segment? I will use a distance formula. Keep in mind again, the arc length between 2 points is always slightly larger than the distance of the segment between those 2 points, because a straight line is always shorter than a curved line involving both of the same points. So I know we have a r cosine theta for an x value, and I know we have an r sine theta for a y value, and I can do the distance formula to compute this segment. I have one set of points and I have another set of points, and I can do y2 minus y1 whole square plus x2 minus x1 whole square, the distance formula, and let's do it. We have a 0 minus r sine theta whole square. This is my y2 minus y1. It doesn't matter if these are your 2's and these are your 1's, or you flip them around, plus x2 minus x1. It will be here r minus r cosine theta whole square. You have to compute this. From here you're just getting a r square sine square theta. But when you expand this, you're getting an r square plus r square cosine square theta, and then the minus 2ab, you know, a square plus b square minus 2ab, that's going to be minus 2r square cosine theta. And now you have to simplify all of that. When you simplify it, this by means of a trigonometric identity, sine square theta plus cosine square theta equaling 1, and isolating the r square is just equal to a r square. You have an r square coming from these two items, and you have an r square over here, and then you have minus 2r square cosine theta. All of this is computing into the length of that segment, this right here, these 2 points being connected by that segment, which I am also symbolizing as this, as you know. And here you have a 2r square minus 2r square cosine theta. You can isolate an r square, and that's what I'll do. I'll isolate an r square and I have a 2 minus 2 cosine theta in the radical. I'll push the r square out as an r. I'll have a square root r square root 2 minus 2 cosine theta, and hence you see this come about. So we're looking here at a quotient of a arc length and a segment length, both being measured by the same angle. Now let's evaluate the limit. Before you evaluate the limit, keep in mind you can cancel out something. You can cancel out the radius component. You have theta approaching 0 from the right, the thetas cancel out. I have a theta divided by square root 2 minus 2 cosine theta. Again, it represents an arc length divided by a segment length. Now when you put 0 here in place of the theta, you have a 0 over 0 indeterminate form. So you want to use the L'Hopital's rule, but I'm going to do some algebraic manipulation. I will square this to get rid of the radical. I'm looking here at this limit applying to every step of this procedure. I won't keep writing it, but you know it applies to everything. I have here a theta square divided by 2 minus 2 cosine theta. When you put 0 in places of theta, you still have an indeterminate form, 0 or 0. So we can do a round of L'Hopital's rule, meaning a derivative with respect to the theta variable. I'm getting here in the numerator 2 theta, in the denominator the derivative of constant is 0, but the derivative of minus 2 cosine theta will be a positive 2 sine theta. You can cancel these 2's out. When you put zeros here in places of theta, you still have a 0 over 0, so you can do one more round, and we will do one more round. You can technically do as many rounds as needed until the indeterminate form disappears. Now when we do the derivative of theta, is just a 1. When we do the derivative of sine theta, I have here a cosine theta, and you can put 0 over here. When you do it, you have a 1 over 1, and that gives us exactly the answer we wanted, and it brings us to a completion. Anytime you're looking here at a sector developing from a unit circle, a certain angles generating the segment and a certain angle generating the arc length, the quotient of the arc length to the segment decreases such that the difference of the two becomes less and less. As the angle approaches 0, the difference of the two independent values become less, but the quotient approaches 1, and that right there is what we are demonstrating in this video, and it comes to an end. Thank you for watching.